Welcome students. Now in this video we are going to see the shear angle. The shear angle and its expression. Okay, so shear angle is represented by the phi. So it is nothing but the angle between the shear plane and the cutting velocity vector. Okay, so let us draw the diagram. The very important and the common diagram in the metal cutting that we are using every time here. So this is this workpiece, this is the produced chip, and this is the tool, isn't it? Okay, so see, if this is the cutting velocity vector we see, and we know that this is our shear plane where actual breaking of the bonds of this material is going to take place and material is shearing. So this is the shear plane, so the angle between this shear plane and the cutting velocity vector we see is our shear angle phi, and we are going to determine the value for the same. Okay, now let us see. We are having some important parameters here. Say this distance, okay, is nothing but our uncut chip thickness T1 or undeformed chip thickness T1, and this is our cut chip which is having the thickness T2. Okay, and of course the width is going to be same before and after cutting, as this is the plane strain condition. Whatever the deformation, okay, we are getting it along the lengthwise direction. Therefore see, the chip length is going to increase but the width remains same. Okay, so it will be lengthwise increase in the chip, okay, not in the width wise. So width of the chip, say suppose B is the length of the width of the chip before cutting, that is B1, and after cutting this is say B2, or I can show it here. This is the width of the chip that going to produce, okay, and this is our tool. So of course this width of the chip before cutting and after cutting, it is going to be same. B1 is equal to B2. Okay, now say if the length of the cut chip is L2 and length of this uncut or undeformed chip is L1, I will write the each and everything here. T1 is what? Uncut or undeformed chip thickness. T2 is cut chip thickness. Now see here, T1 is in the form of undeformed chip. T1 is the thickness of this undeformed chip, which is going to deform like this. When it deforms, the thickness become T2. Okay, and this is the feed given to the this tool, isn't it? So if this velocity of this tool with respect to this workpiece is our cutting velocity we see, then here the chip is flowing with the velocity say Vf. Chip is flowing with velocity Vf, that is the chip velocity. Vc is what? Our cutting velocity, and Vf is our chip velocity, or this also called it as the flow velocity. flow velocity. The velocity of chip with respect to the tool, it is the flow velocity or chip velocity. Now see, if we apply the volume constancy principle, yes, it is valid here in metal cutting also, as the volume of material before cutting is equal to volume of material after cutting. So whatever the volume of chip which is inside this material in the undeformed condition, that volume will be equal to this volume after cutting condition, after cutting operation. Okay, so the volume of chip that you can observe here is equal to volume of chip which is present here in the workpiece in undeformed manner. Okay, so if you equate both of these, what we can write? We can write, say, B1 T1 into L1 is equal to B2 T2 into L2. So see, B1 into T1 into this length is equal to this B2 T2 into the length of the chip. So as we know that there will be no flow in the widthwise direction, only along the length of the chip is going to increase. So B1 B2 is nothing but same, so get cancelled. So what we get, T1 divided by T2 is equal to L2 divided by L1. Okay, so this is the one ratio we got here. This T1 divided by T2 is very important ratio, that is known as the chip thickness ratio. Chip thickness ratio, or this is also known as the cutting ratio. The cutting ratio, chip thickness ratio or cutting ratio, or chip compression factor. This is also known as chip compression factor. Very important term. We will see in many of the cases in the questions we are required this ratio T1 by T2, and it is represented by the small r. How this T1 by T2 is represented by small r. This T1 by T2, that is nothing but our chip thickness ratio, which is equal to the uncut chip thickness divided by cut chip thickness is equal to cut length of chip divided by uncut length of the chip. So definitely this r is always less than 1. This r is always less than 1. Now if we take this reciprocal of r, that is nothing but zeta, it is 1 upon r, known as the chip reduction coefficient. What it is called as chip reduction coefficient, that is represented by zeta. Okay, so this ratio is very important, this r and this zeta. R is chip thickness ratio, zeta is chip reduction coefficient. Okay, so try to get it clear. Now see, this r we can also write in the terms of this cutting velocity and flow velocity. If we equate the volume flow rate before cutting and after cutting, how we can have that? So I can write volume flow rates before cutting B1 into T1 into cutting velocity Vc. If I equate with this B2 into T2 into flow velocity of chip, isn't it? So B1 and B2 get cancelled, so T1 divided by T2 I got it as Vf divided by Vc. So this is also nothing but the chip thickness ratio R can be written as Vf divided by Vc, isn't it? So in how many manner we can write this R is equal to T1 divided by T2 is equal to Vf divided by Vc is equal to L2 divided by. So please remember this. So sometimes if you are not available with the cut length of the chip, so in that manner, in that condition, what we can do? So we can do one thing. So if the cut length of the chip is not available with us, we can have the weight of that chip. Okay, so how we can write the weight? Suppose L2 is not available with us, is not available, then what you are going to do? You are going to measure, we are going to measure the weight of the chip. Weight of the chip, isn't it? So what is weight? Weight is nothing but mass into this gravity g. But mass is what? This volume into density of material into g. So volume is what? For the chip, it will be, you can have the weight. Weight is available with you, and from this weight we can have volume is nothing but this area into length. This length is nothing but length of chip into rho g. It is nothing but the W is the width of weight of chip. So area of chip is what? So area of the produced or cut chip is nothing but this B into what? Thickness. Width into thickness of the chip is nothing but our area, isn't it? So you can write here this length of the cut chip L2 is equal to W divided by this rho into B into T2 into this G, isn't it? So we can able to calculate the length of the cut chip also, isn't it? By if you have just only the weight, if you measure the weight of the chip which is produced, so from that also you can able to find out the L2, and then you can have the ratio L2 by L1 as our chip thickness ratio. Okay, fine. Okay, so after that, say I am going to do some geometry here. So what I am going to do, say I will write the names here, so O, A, B, and from A onto this rake face of the tool I am going to draw a normal, okay, say at point C. Okay, so here if I draw the normal here at onto the rake face of the tool, and this angle is alpha, so of course this angle will be what? 90 minus 5. This angle will be 90 minus 5. So total angle AOC, this angle AOC will be how much? This alpha plus 90 minus 5. So you get this angle AOC as alpha, this rake angle, plus this angle 90 minus 5. Now tell me what is this angle OAC? What is the angle OAC will be? This 180 minus this 90 minus 5 minus this alpha, isn't it? So this is 180 minus again this minus 90, isn't it? So it will be 90 plus 5 minus alpha minus 90, so it becomes only 5 minus alpha. Okay, so this angle OAC becomes what? This is 5 minus alpha. Okay, so see here, in triangle OBA, this is 90, and I will write this OA is nothing but our what? O is our LS, which is equal to length of shear plane. So in triangle OBA or ABO, what is this sine of phi? Sine of angle phi is equal to AB divided by OA. AB divided by OA. And AB is what? Our uncut chip thickness T1. So T1 divided by OA is nothing but LS. So LS here is equal to T1 divided by sine phi. So this is equation number 1. Okay, and in triangle OAC, what is of angle cos of phi minus alpha? Cos of phi minus alpha is equal to what? This AC divided by OA. AC divided by OA. Now what is AC actually? This is nothing but this cut chip thickness, that is T2 divided by OA is LS. So here what you can write, LS is equal to T2 divided by cos of phi minus alpha. Say this is equation number 2. So here the first thing you are getting here, that is how to calculate the length of the shear plane when you are having this shear angle phi and the uncut chip thickness or cut chip thickness. You can able to calculate the length of shear plane here, isn't it? Now say this is also length of shear plane, this is also length of shear plane. If I equate equation 1 and 2, what I can write? Equate equation 1 and equation 2. What I will write? T1 divided by sin phi is equal to T2 divided by cos of phi minus alpha. So now one more relation we are going to get for the chip thickness ratio R, which is equal to T1 divided by T2 is equal to sine of angle phi divided by cos of angle phi minus alpha. And you know that T1 by T2 is R. That is R is equal to sine phi divided by cos of phi minus alpha. Or I will write 1 upon R. That is what T2 divided by T1 is what? 1 upon R is equal to cos of phi minus alpha divided by sine of phi. Now if you expand this cos of A minus B, that is cos of phi minus alpha, what you can write? Cos A cos B plus sine A into sine B. B is what? Alpha. Divided by sine phi. So therefore 1 upon R is equal to what I can write? Sine phi divided by cos phi divided by sine phi. This is cot of angle phi into cos alpha plus sine phi get cancels. So only sine alpha is there, isn't it? So if I simplify this, so what I can write? That is 1 upon R minus sine alpha is equal to cot alpha into cot phi, isn't it? So 1 minus R sine alpha divided by R, take here cos alpha, no? So cos alpha take here into cos alpha is equal to cot phi, and reciprocal of cot is nothing but tan. So therefore we can write tan of angle phi is equal to R cos alpha divided by 1 minus R sin alpha. Very important formula for calculating the shear angle phi. How to calculate phi is nothing but tan inverse of R cos alpha divided by 1 minus R sin alpha. Very important formula. Please remember for the shear angle phi, where R is what? R is our chip thickness ratio, and alpha is our rake angle. Please remember. When say here, when this rake angle is 0 for the tool, what is the standard case you are getting? That is tan phi is equal to cos 0 is 1, sin 0 is 0. So you are getting here tan of phi is equal to R only. Okay, when back rake or rake angle is equal to 0. Isn't it? So this is the formula, very important formula for the numerical purpose. Many times we require this first value of shear angle phi. Understood how to calculate the shear angle phi? It is equal to tan inverse of r cos alpha divided by 1 minus r sin alpha. Please see it. Thank you.